Hello, class. We are about to start section 405, which is actually on page 371. Okay, lesson 405. The title is An Average Joe. Our learning objectives is to compute measures of average for given data, to interpret the story told by measures of average, and to compute and interpret the mean for group data, compute weighted grades, and use technology to compute measures of average. Let me see if I could get this in a little bit closer. All right. Now, it says, are you an average college student? What does that even mean? According to a variety of sources found on the web, the average college student is 20 years old, lives on campus, and works off campus during the school year. She is female, talks to her parents every day, and comes from a family with an annual income between $50,000 and $100,000. She sleeps 6 hours a night, has $2,700 in credit card debt, and will leave college with $21,000 in total debt. If this doesn't sound exactly like anyone you know, don't feel bad. As we will learn in this lesson, the word average is ambiguous. There are a variety of ways to describe an average. So what one source considers average might not match someone else's thoughts. And with so many different facets to a person, it's possible that nobody exactly meets all of the average criteria. Okay, so we're going to go over here to page 372, which is the next page. It says, here's the salary list for Vandelay Industries, which we'll use to study measures of average, which are more technically called measures of central tendency. Now, if you notice here, most of these names here are Seinfeld characters. Okay, the mean. There's a pretty good chance that when you think of average in a math class, what you're thinking of is actually called the mean. The mean, also known as the arithmetic average, is found by adding the values of the data and dividing by the total number of values. Here's a good way to think of the mean. If all of the numbers were equal weights put on a number line, the mean is where the number line could be balanced without tipping in one direction or the other. The Greek letter sigma is used to represent the sum of a list of numbers. If we use the letter x to represent data values, then the sum of x means to find the sum of all values in a data set. Using this notation, we can write a formula for finding the mean. Okay, so we have the formula for finding the mean. It's basically the sum of x divided by the amount of numbers you have. Okay, so it says find the mean salary for the company. Now what I'm going to do here, I'm going to write this out, but I'm actually going to solve it using Desmos. So if we take the salaries of the company, we have 58,000 plus 65,000 plus 944,000 plus 20,000 plus 52,000 plus 51,000 plus 53,000 plus 55,000 and then plus 50,000. And now this is all divided by, we'll count how many values we have here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So this will all be divided by 9. So I should put mean is equal to. All right, so now we have these values. We need to put these in our calculator. All right. Well, I guess I could just do it like this. So I have 58,000 plus, well, I should have did the division. Hold on, let me backspace here. So 58,000 plus 65,000 plus 944,000 plus 20,000 plus 52,000 plus 51,000 plus 53,000 plus 55,000 plus 50,000. And then that's all divided by 9. So that would give us, if we round to 2 decimal places, I'm going to write it here because I ran out of space. So the mean is equal to, it'll be $149,777.78. That will be your mean, or the average. Okay, now it says number 2, Newman owns the company and obviously pays himself a handsome salary. If we ignore Newman's salary, what is the new mean based on this? Do you feel like the mean is a good measure of what the typical employee makes? Okay, so basically, we will have all of these salaries except for the $944,000 salary. And that is going to make a big difference here. And it'll be divided by 8 since we took out Newman's salary. So the mean. Now, this is one thing I like about Desmos. We could come right up here to Desmos, and we could go right here and take out the 944,000. And then it would give us, oh, and we have to change that 9 to an 8. And it will give us the new average, or the new mean. So it'll be $50,500. Does everyone follow that? Okay. Now, I want to show you another way of doing this that will make this easier for us later on. We're going to do a table. And in this table, we're going to put in the values of everyone in the company. We don't have to worry about the Y1 part. We'll just do the X1. So we add the 58,000, the 65,000, the 20,000, the 944,000, 52,000, 51,000, 53,000, 55,000, and the 50,000. Okay, now, what's going to be significant about this is once we put all these values in here, we could go right here to this table, this keypad, go over here to functions, and as you see, we have what is the stats tab here. You could click on stats, and you notice here it has mean. And then what you could do, since the table, all these values are in X1, we could type in X of 1. And you notice here it gave us the answer that we had here for number 1. Now, if we want to do it without the 944,000, we could go right up here to this table and take out the 944,000, and then it adjusted the mean. But I'm going to type the 944,000 back on here. Okay, so that is the complete table for us. And a lot easier than writing out all of this here when we could just put it in here. Okay, so now we move on. We go on to the next page. The next item we come to here is called the median. Now it says here, according to the National Organization of Realtors, the mean selling price for existing homes nationally in August 2015 was $271,600. The median selling price, on the other hand, was $228,700. Since both of these are measures of central tendency, how can they be so far apart? What exactly is the median? In this case, the median tells us that half of all homes sold during that month were priced above $228,700, and half were priced below that amount. In short, the median of a data set is the value in the middle if all values are arranged in order. The median will either be a specific data value in the set or will fall in between two values. Here's how we find a median. Arrange all of the salaries at Vandelay Industries in order from smallest to largest. So the smallest value would be the 20,000. Then we would have 50,000, 51,000, 52,000, 53,000, 55,000, 58,000, 65,000, and then the 944,000. Okay, now it says find the salary that's right in the middle of your order list. That's the median salary. Okay, we have 9 values, so the 5th value is right in the middle. So that would be the median is equal to 53,000. Okay, now if there is an even number of values in a data set, there will be 2 values in the middle, not one like in question 4. How do you think you find the median in that case? What you would do is find the average of the 2 middle values. All right, now, before I move on, I want to show you something here. Okay, as you notice here on this table, this is out of order. But even though it's out of order with Desmos, you don't have to have it in order to find the median. We can go back here to function stat. You see median, and then you would type in x1. And it gave you the 53,000 that we got for number 4. So Desmos actually does the calculations for you. Now we come here to page 374. It says finding the median of a data set. We've already went over these steps. You arrange them in order from smallest to largest, and you pick the value in the middle. And then step 2, if it's not an odd number of values, like instead of being 9 values, it's 8 values, you would take the middle 2, add them together, and divide by 2, which is the average of the 2. So we'll take a look at that with number 6. It says find the median of the salaries at Vandelay Industries without Newman's. How does it compare to the median of the salaries with Newman's included? Okay, listen. We know Newman's is the largest salary. So let's go back here. They're saying if we took this out, we will only have these 8 values here. Now, if you look at these 8 values, the middle 2 values is this 52,000 and 53,000. Because if you box these in, they have 3 below it, 3 above it when you don't count Newman's salary. So these 2 are in the middle. So what you're supposed to do according to the directions, you're supposed to take that 52,000 and add the 53,000 and divide it by 2. Now that will end up being 105,000 divided by 2, which is 52,500. That will be your median. And I should have put median is equal to. Okay, now it says, how does it compare to the median of the salaries with Newman's included? It is not affected by that much. Because remember, with Newman's included, the median was 53,000. This only went down $500, so it's not that big of an effect. Okay, number 7. What does this tell you about median when there are outliers? Sample data values that are very far away from the majority of the values. Now, 944,000, which is Newman's salary, is considered an outlier because the highest salary before that was only 65,000. So that is definitely an outlier. So what we would say is outliers have little effect on the median. Now, as we saw earlier, it had a big effect on the mean, but little effect on the median. All right, number 8. It says find the median of the salaries at Vandelay Industries without Newman's if Kramer quits to start his own company, the Peterman Realty Tour. What can you observe? Now listen, going back here, Kramer's salary is the second highest salary. So they're asking if you got rid of these two salaries, what would the median be? But if you got rid of those two, it'd be 7 values here. So the middle value of the 7 values would be this 52,000. So the median is equal to 52,000. The median still does not change much, even though the two highest salaries are removed. Okay, so if you notice here, of the two, between median and mean, median is not affected that much by outliers. Okay, so now we're going to go over here to page 375. Now on page 375, we have what is called the mid-range. The mid-range is another measure of average. The advantage of the mid-range is that it's very quick and easy to calculate. The disadvantage is that it totally ignores most of the data values, so it's not a particularly reliable measure, but in a pinch, it could give you a rough idea of average. Now, number 9, it says find the number halfway between the lowest and highest salaries at Vandelay Industry. That is the mid-range. So basically, the mid-range is calculated by taking the lowest salary plus the highest salary divided by 2. Now, when you take these two values and divide it by 2, it'll give you 482,000. That is the mid-range. Now, it gives you the steps of the mid-range here. But if we look here at number 10, it says find the mid-range of the salaries at Vandelay Industries, excluding Newman's. How does it compare to the mid-range of all salaries? So this mid-range, the smallest value would still be 20,000, but now the highest value would be 65,000 because Newman's is gone. So it'll be 85,000 divided by 2, which is 42,500. And this is a much lower mid-range. Okay, number 11. Explain why the mid-range isn't very reliable as a measure of central tendency. The mid-range is affected too much by outliers. There was a significant difference between having Newman's salary in and not having it in. It was over 10 times more by having Newman's salary in there. So it is affected quite a bit by outliers. Okay, now We move on to the next page. We come to the mode. Now the mode basically goes like this. It's the number or numbers that appears the most. And so what we do, if all numbers only appear one time, then it would be said to be no mode. But if you look here, the mode, the number that appears the most here is 12. 12 appears 1, 2, 3, 4, 5, 6, 7 times. It appears more than any other value. So your mode is 12. Now, how does the mode compare to the mean? What do you think describes the typical case best? Okay, the mean, we're not going to take up a lot of time, but the mean, when you add up all of these numbers, it'll give you 258, and there's 20 values. So that'll give us 12.9. And we could say they are both similar. So they are fairly equal. Okay, now we come down here to problem 14. The number of wins in a 16-game season for the Cincinnati Bengals from 1996 to 2014 is listed below. Find the mode. Now, the mode. If you look here, the mode will be 4 and 8. Because if you look here, let's start off with the 4. 4 appears 1, 2, 3, 4 times. 8 appears 1, 2, 3, 4 times. Nothing else appears that many times. So your mode here would be 4 and 8. So that lets you know that you can have no mode, you can have one mode, or you can have more than one mode. Okay, 15. How does the mode compare to the mean? So we have the mean is equal to, we add all these numbers up, it'll be 134 divided by 19, which would be 7.1. So it says, discuss again, include a description of which measure of central tendency you think is more reliable in general and why. The mean is better because the mode has two values instead of one. Because if I ask you what is the measure of central tendency and you give me two different numbers, that is not going to help me. But having one exact number does help me when we're talking about calculating values. Okay, now we move on to the next page. And I believe with 4 or 5, I think we only have like about 3 or 4 more pages to go for 4 or 5. Okay, now for 16, it says, do the employee salaries at Vanderlei Industries have a mode? And the answer would be, is no mode. Because all their salaries or odd numbers appear only once. So if all the numbers appear only once, is no mode. That's the only time you have no mode, is when all the numbers appear only once. Now, the mode is probably most useful when data are classified by groups or categories. In fact, it's the only measure of central tendency that even makes sense when the data values aren't numbers. It says a survey of the junior class at Fiesta State University shows the following number of students majoring in each field. Find the mode. Now the mode, now they have the major, but what you would do is look at the number. Whichever one has the highest number in that major, that's the mode. So the mode here would be business. It says, now, let's evaluate the average salary claim made by Vandelay Industries at the beginning of this lesson. How truthful do you think that claim was? Use the measures of average you found in this lesson to discuss whether or not you think they were being deceptive anyway. Okay, the mean, which we found out with Newman's salary, was $149,777.78. The median was 53,000. And then finally, well, the mid range was 482,000. And then the mode was no mode. Now, based on the mean, they were technically truthful. But we know about technical truth. But considering the actual salaries, it is misleading. And I would say this, there's no way that the owner of the company's salary should be included with the regular workers, as the workers will never make as much as the owner does. Okay, now we move on to the next page. We come here near the middle, because we want to find the mean for group data. Okay, it says step 1, find the midpoint of each class in the group data. Multiply the frequency for each class by the midpoint of that class. Add up all of the products from step 2. Divide by the sum of all frequencies. All right, and this is the formula here. Now, first of all, when they ask us for the midpoint, they're asking us for the midpoint of the class. So you could do it the easiest way to do it is to add the two values up and divide by 2. The lower limit and the upper limit. This would be 204 divided by 2, which would be 102. This right here would be 214 divided by 2, which is 107. Now, before we go on, if you look at the lower limit, you notice they're going up by 5. If you go to the upper limit, they're also going up by 5, which is the class width. So your midpoint also will go up by 5. So this would be 112, 117, 122, 127, and then 132. Now, they're telling us next we will multiply the midpoint by the frequency. And that will give us these values here. So let's take our calculator and let's type in these values. We have 102 times 2. We have 107 times 8. We have 112 times 18. 117 times 13. 122 times 7. And then the other ones we don't really have to do because they're times 1. So let's write this out. This would be 204. This would be 856. This would be 2016. This would be 1521. This would be 854. This would be 127. This would be 132. Now we need to add all of these values together. So let me go down here to this next line. All right. So we add all these values together: 204, 856, 2016, 1521, 854, 127, and 132. All right, so this would be 5,710. Let me make sure that I have all the numbers correct. 132, 127, 854, 1521, 2016, 856, 204. All right, so we got 5,710. So to find the mean, we would take our 5,710 and divide it by how many values we have. We can add up the frequencies, and that would be 28, what's that, 41, 48, 49, so 50. So there's 50 values. So we take 5,710 divided by 50. So this will give us 114.2. That would be the mean. All right, now we move on to the next page. Now it says, explain why this formula only gives an approximation to the mean, not the actual mean. Because we do not use the exact numbers, we use an approximation of the numbers. So that's why we don't get the exact value, because we're using approximations. Now, our next thing here, we're going to be dealing with what is called weighted means. So if you notice here, it says finding the mean for group data is similar to finding a weighted mean. We can illustrate the concept by finding a student's average score in a course where different components contribute different amounts towards the final grade. For example, let's look at the grading structure for one course. Homework average is 50 points, 4 tests 30 points each, final exam 50 points, group project, and then attendance and participation. Now it says here, Tong had 87% homework average, got 91%, 82%, 86%, and 94% on the 4 tests. 88% of the final exam, 92% on a group project, and 100% of attendance and participation points. We could treat this as a weighted mean problem to find her overall average percent. The number of points assigned to each component of the course acts as the frequencies for each class, and the percentage earned on each component plays the role of the midpoints for each class. Then we can use our procedure for approximating the mean for group data. Number 3, with that in mind, what role does the sum of the points for each component play in the weighted mean calculation, and why? The sum of the points is like the total number of data values or n, because n represents the data values, because each number of points is like a frequency. Now, if we look at number 4, it says use the mean for group data formula to find Tong's average for the course. Okay. First of all, we know we're going to be dealing with a fraction here. So get 50 points for the homework average, but he scored at, or she scored at 87%. So it'd be 50 times 0.87 plus, now we look here at the test here. Remember, we get 30 points each for the test. So it'd be 30 times the 91% plus 30 times the 82%, then 30 times the 86%, and 30 times the 94%. And then plus, we got an 88% on the final, Now the final is worth 50 points. So it'd be 50 times 0.88. And then a 92% on a group project. The group project is worth 20 points. So that'll be 0 times 92%. And then finally got 100% for participation. Now remember, participation is worth 10 points. So it'd be 10 times 1, because 100% we know is 1. Now we're going to divide all of this. Now we have to divide this by the total points. So we have 50 points plus, now remember it's 30 points each for 4 tests. So 30 times 4 is 120. And then the other 50, 20, and also 10 points. Now, we're going to put this all in our calculator. So, we'll do 50. I'll do the division sign. So 50 parenthesis 0.87. And then plus 30 times 0.91 plus 30 times 0.82 plus 30 times 0.86 plus 30 times 0.94 plus 50 times 0.88 plus 20 times 0.92 plus 10 times 1. We really didn't have to put that, but okay, now for our denominator, we have 50 plus 120 plus 50 plus 20 plus 10. So that would give us 0.8872. But remember, we want to write this as a percent. So it'd be 88.72%. And that would be your weighted mean or weighted average. Okay, so now we move on to the next page. It says, what are the pros and cons of each of the measures of average we studied? Okay, I'm going to just give one of each. The mean, it uses all data. That's a pro. And then the con is outliers affect the results. Okay, now the mode gives common case. That is the pro. The con, it ignores extreme values. Okay, the median. The pro is not sensitive to outliers. The con, it ignores extreme values. The mid-range. The pro is it's easy to calculate. The con uses only 2 numbers. All right, number 6. This is my favorite question in the whole lesson. Look back at the description of the average college student in the opening paragraph. For each characteristic listed, write which measure of average you think was used. Okay, now, for the 20-year-old, that's the age. That could be the mean, could be the median, and it also could be the mode. Could be 3. Lives on campus. I think that'd be more so the mode. Female, I think it'd be mode. I think it could, well, okay, talks to parent every day, be the mode. Annual income would be the mean, then also the median. Let's see, sleeps 6 hours, the mean and the median. And then $2,700 on credit card. And that's the mean and the median. And then 21,000 total debt is also the mean and the median. Okay, now that is basically it from section 4.5. We're about to move into section 4.6 in just 1 second. Okay, class, we're about to start on section 4.6, and the title is Your Results May Vary. The learning objective is to compute measures of variation for a given data set, to interpret standard deviation for a data set, make meaningful comparisons of standard deviation for two data sets, and to analyze the procedure for computing standard deviation. Now at the bottom here, the simplest measure of variation that we'll study is the range. The range of a data set is the difference between the largest and smallest values in the set. So the range is the largest value minus the smallest value. Okay. So now we will go over here to page 390. All right. The first list below is the weights of the dogs in the first picture, and the second is the weights of the dogs in the second picture. Find the mean and range for each list. Okay, so we'll mark this as the first. So the mean, we add these values up. That'll give us 261, and it's 4 values. So this will give us 65.25, and this is pounds. Okay, now the range. We would take the largest value, which is 73, minus the smallest value, which is 58. So it'd be 15 pounds. So now we go here to the second. The mean, we would add these values up. It'll be 512 divided by 8, which will give us 64 pounds. The range, we look here, the largest value is 125 minus the smallest value, which is 30. So that'll be 95 pounds. Okay, now number 2, describe what you notice about the range and mean for each group of dogs. The means are similar. One is 64, one is 65.25. They're similar. But the range is significantly different. So their variation is different. Okay, number 3. Why is the range somewhat limited as a measure of variation for a data set? That is because it only uses the largest and smallest values and ignores all others. Okay, now we move on to page 391. Okay, we come to standard deviation. The range is a limited measure of variation because it ignores all the data except the highest and lowest values. If most of the values are similar, but there's just one unusually high value, the range will make it look like there's a lot more variation than there actually is. For this reason, we will next study standard deviation, which is a much more reliable and commonly used measure of variation. Standard deviation is a little tricky to compute. Eventually, we'll learn how to use technology to handle the computation, which will allow us to focus on interpretation. But first, we'll develop a procedure for computing standard deviation by hand. This turns out to be more useful even if you never actually do compute it by hand, as it really helps you to understand what exactly standard deviation measures. This is a bit of an oversimplification, but it's still very useful in understanding what standard deviation is designed to measure. Standard deviation essentially describes the average distance that each data value is away from the mean. Read the description of standard deviation in italics above carefully again. Why does standard deviation provide a very reasonable way of describing how spread out a data set is? That's because it considers every value. Because remember, when you're dealing with the mean, you consider every value and how far they are, well, they spread out from the mean, which is kind of a center value. A standard deviation that's large relative to the mean tells us that the data values vary pretty widely from the mean. A relatively small standard deviation means that most data values are clustered fairly close to the mean. Okay, so what we're going to do, we're going to skip to page, let's see, what page is that? We're going to skip to page 396. Let's go to page 396. Here we go. It says the table below shows the number of arrests in the United States for possession of marijuana in thousands for the years from 2005 to 2014. All data was gathered from the annual Uniform Crime Report published by the Federal Bureau of Investigation. Find the mean and sample standard deviation for the number of arrests, include units. Okay. Now they tell us that this goes from 2005 all the way up to 2014. So what we're going to do, we're going to use Desmos. We're going to do a table. Let's add a quick table here in Desmos. Now remember, it says from 2005. So that means 2005 is our zero value. 2006 will be 1, 2007 will be 2, and so on. Let me see. So that's 5, 6, 7, 8, 9, 10, 11, 12. All right, 13 and 14. All right. All right, now we need to put in our data values. So for 2005, those were 569. Okay, so we put in all of our data values. Now it says they wanted the mean and the sample standard deviation. So if we click down here, we'll go back to functions and stats, and they wanted the mean. Now if you notice here, Y2 is what we're actually looking at as far as the data is concerned. Now Y2, we'll put Y2 here, and the mean is 500. Now one thing you need to know too is this here. The mean symbol is the X bar, and we'll talk about that. It's 571.3. And that means, because this is in thousands, that means that it was 571,300 arrests. Now, we want the standard deviation next. We can go right here to function. And right here you see where it says standard STDEV. That's standard deviation. And we'll put in Y2 as well. So your standard deviation, the sample standard deviation has a lowercase s, and that is 48.7, which is really 48,007, excuse me, 700 arrests. Now, it says, why was it appropriate to find sample standard deviation rather than population? If we are trying to generalize a larger set of years, then this is only a sample. Now, before I finish out this page, I notice here that we had actually skipped over one thing that I was supposed to take a look at with you. If you go back to page 394, I was supposed to go over this formula with you. This is the formula for the sample and population standard deviations. With the sample, you have a lowercase s, and that is equal to the square root of the sum of x minus x bar. Now this x bar is the mean of the sample, squared over n minus 1. Now this is lowercase, I believe this is lowercase beta, is equal to the square root of the sum of x minus mu squared over n. And it tells us what each of these symbols mean. The x represents each data value. The x bar is the mean of the sample. So the mu is the mean of the population. So both of these are defined almost the same. One of them is for a sample, one of them is for a population, but they're both mean. N is the number of data values in the sample. N is the number of data values in the population. So if you notice, these letters are kind of interchangeable, but if you notice these letters here, some of them are a giveaway as to which one you're using. So if you see the X bar, you know you're using sample. See the mu, you know you're using population, and so on. So that's where we have some of our terminology from. So I just wanted to make sure that we actually hit on that. All right, now we go down here to number 3. It says find the coefficient of variation for the preceding arrest data. What percent of the mean is the standard deviation? Now we're back on page 396. So we have C of V, the coefficient of variation, is the sample standard deviation over the sample mean. And then here we have the population standard deviation over the population mean. So here it says find the coefficient of variation for the preceding arrest data. What percent of the mean is the standard deviation? Okay, so we have C of V is equal to, this would be S because we know we use the sample up here all over the X bar. The sample was 48.7 sample standard deviation all over the mean, which is 571.3. We put that in our calculator and we'll get 0.085, which is 8.5%. So the standard deviation is 8.5% of the mean. Okay, now we go over to the next page. It says, do you think the standard deviation and coefficient of variation for this data set will be more likely to be used in an argument by someone that is in favor of legalizing marijuana or against? It can be used either way because the low percent would have people for legalization say it is a small number. Why bother arresting people? On the other hand, people against it will say law enforcement is doing well by keeping the number low. So it depends on what side of the argument you on. You could argue it either way. Okay, now for this next value here, or the next problem, it says find the coefficient of variation for the 8 dogs from questions 5 through 11 in the class portion. Compare it to your answer to question 3 on the previous page. Now, these are the values we had from the other page, 30.7 pounds. So the coefficient of variation would be 30.7 all over 64, which is 0.48, which is 48%. Now, this is from the previous exercise when we did that list of the dogs. So if you look here for number 3 we just did on page 396. Number 3 coefficient of variation was 8.5%. So the dog data varies much more than marijuana arrest. Because you got 48% here for the dog data, but only 8.5% for the marijuana arrest. Now, it says for questions 6 through 8, identify the data set that is likely to have a larger standard deviation. Make sure you explain your reason, like with sentences and stuff. Okay, data set 1, data set 2. If you notice here, if we look at the range of values, data set 2 has a larger range. So it would be expected to have higher variation. Now, number 7, data set 1, 40-yard dash times for starting running backs in the National Football League, or data set 2, 40-yard dash times for every student in your math class. Now, data set 2 will vary more than data set 1 because of different fitness levels in an average class, as opposed to fitness levels of professional athletes in the same position. As you would expect that if they're a starting running back, that their times will be very close as far as their speed and stamina and everything. Okay, now, problem number 8. It says data set 1, average monthly high temperature in Chicago, average monthly high temperature in Los Angeles. So data set 1 would vary more because of Chicago's winters. Okay, number 9. A professor has 2 sections of Math 115 this semester. The 8:30 a.m. class has a mean score of 74% with a standard deviation of 3.6%. The 2 p.m. class also has a mean score of 74%, but a standard deviation of 19.2%. What can we conclude about the student averages in these sections? We can conclude the 8:30 class, a.m. class, scores are similar and vary slightly. The 2 p.m. class scores vary significantly and will be very different. Okay, now basically if you look at it like this, if I have a class that say the average score, like they said the average score was a 74% with a 3% variation. Okay, so that's the same as saying one person got a 77 and another person got a 71. If you add a 77 and a 71 together, let's take a look here. So you have a 77 plus a 71, and you divide by the two scores, you'll get a 74, 74%. But watch this. The other class, there's a 19% difference, and I'm just rounding to the nearest whole number here for that. It's a 19% difference. So let's say that someone got, let's see, a 96%, and then someone else in that same class got 52%. And we divide that by 2. And you notice we have the exact same score. But this is the difference. Like here, the scores in the 8:30 a.m. class, their scores would be very close, 77, 71. I mean, there's a difference, but not that great of a difference. But a 96 and a 52, there's a great difference there. All right. Now we are done with section 4.6. Now we're about to go to the last section of this course, which is 4.7, which starts on page 405. Okay, the title for 4.7 is Just a Normal Day. All right, now, our learning objectives. It says to recognize characteristics of data that are normally distributed, understand the connection between area under a normal curve, percentage, and probability, make an educated guess about the empirical rule, then use the rule to calculate percentages and probabilities. Compare data values from different sets using z-scores. All right. If we go down here to number 1, it says list some things that you think might be normally distributed. Try not to focus strictly on physical sizes. I think IQ scores, finish times in a race, scores on an exam. So I think those will be normally distributed. Okay, now we come here. It says, suppose a researcher selects a random sample of 100 adult women, measures their heights, and constructs a histogram. The researcher would probably get a graph similar to the one shown below. Notice that we omitted a scale on a horizontal axis. Put in a scale that you think seems reasonable based on the description of this histogram. What do you think the value right in the middle of the horizontal axis represents? Let's do some heights here. Let's start off with this last one. We can make this person 4 feet 7 inches. This person 4 feet 10 inches. This person 5 feet 1 inch. Then 5 feet 4 inches. Then 5 feet 7 inches. Then 5 feet 8 inch. No, 5 feet 10 inches, not 8. And then finally 6 feet 1 inch. Okay. What do we think the middle value is? I think the middle value is the mean. Next, the researcher decides to go big or go home, and she chooses big. She dramatically increases the number of women in the sample. And since she has more data to go on, makes the classes narrower as well. Happy with the result, she adds even more women to her sample and makes the classes even narrower. The result would most likely look like the next two graphs. Okay, now it says, now let's use some imagination. Suppose that our researcher has magical powers and can continue adding data and improving her histogram until there are infinitely many data points. Wow, that's a lot. Instead of drawing boxes, draw a smooth curve that you think the histogram would become in the long run. Now I'm going to try and draw this smooth. Now let me see. This is what I think it'll kind of look like in the long run. Okay, now we go to the back here. Problem number 4. It says if all went well, you've just drawn your first normal probability distribution. We'll see plenty of examples in the remainder of the lesson if you're unsure how well you did. How does the drawing relate to the maple seed pod example from the opening paragraph of this lesson? Now, if you look here at this maple seed pod, this is from page 405. It's almost looked similar to what we had. So we could say very similar. The largest number is in the middle, which we could go back and take a look. Largest number is in the middle, and less on either side of the middle value. And we can see that here. Large, and it goes down. Large, largest, and it goes down. All right. It says a probability distribution that plots all of its values in a symmetrical fashion, and most of the results are situated around a probability's mean is called a normal distribution. Values are equally likely to plot either above or below the mean. Grouping takes place at values that are close to the mean and then tails off symmetrically away from the mean. Okay, now let's look down at number 5. What is the mean height for American women? If you look here, this is in the middle, so that'll be 63.7 inches. Okay, so now we go on to the next page. Now, if we look here at number 6, it says, what percentage of American women are between 57.4 inches and 59.1 inches? 57.4 to 59.1 is 0.034. We just changed that to a percent. So it'll be 3.4%. If there are 31,806 women in the stands for a college football game, how many of them would you expect to be between 63.7 and 66 inches tall? Now, if you look here, back here on the previous page, 63.7 to 66 inches is 0.303. So we will write that, and we'll change that to a percent. Well, we actually don't have to, but this is what the percentage was, 30.3%. Now, they want an actual number here because we have 31,806 women, and we want to make sure that they fall in between this range. So we'll multiply this by the 0.303 or the 30.3%, and that will give us 9,637 women when we round to the nearest whole number. So that will be your answer. Okay, now it says, so now we know that if we have data values that are normally distributed, and if we can find an area under portions of the graph, we can find a percentage of data values that fall in a certain range. That leads to the big question. How in the world do you find areas under the graph? In this lesson, we'll rely on a known rule that allows us to quickly find a range in which most of the data values fall. It's known as the empirical rule. Before seeing the rule, let's make some educated guesses. According to the recent research, the mean height of women in the U.S. is 63.7 inches, which you already knew, and the standard deviation is 2.7 inches. The normal graph below is marked with the mean and heights that are 1 and 2 standard deviations above and below the mean. So we look here, okay. Now on the back here, it says the total shaded area under an entire graph is 1. And this is true for any normal distribution. Explain why. Think carefully about what we know regarding area under a normal curve. Okay, listen. The area represents the percent or percentage in the range. All possible values under the curve must equal 100% or 1. Now, we look here at number 9. It says make an educated guess as to what percentage of the total shaded area is between 61 and 66.4. What does this tell us about women's heights? Okay, so it says 61 to 66.4, 61 to 66.4. I would say that looks about 60%. I would say maybe around 60%. This percentage of women in the population are between 61.0 and 66.4 inches tall. Now, number 10, it says, based on the answer to question 9, estimate the percentage of area between 63.7 and 66.4. 63.7 and 66.4. I would say since I say it's about 60 here, that's half. So I would say about 30%. So next, it says, now make an educated guess on the percentage of total shaded area between 58.3 and 69.1. 58.3 and 69.1, I'm thinking that's about 90%. So I say about 90%. Now, it says, now it's time to see how you did. Now let's look here at the empirical rule. When data are normally distributed, approximately 68% of the values are within 1 standard deviation of the mean, approximately 95% are within 2 standard deviations of the mean, and approximately 99.7% are within 3 standard deviations of the mean. Okay, we'll take a look here. This is the same chart here, but this time it includes the percentages and also the standard deviations. Now, if you notice here, with those standard deviations, you have the X bar right in the center, which is your mean. And then this value here is 1 standard deviation below. This is 1 standard deviation above. Then 2 below, 2 above, 3 below, 3 above. And they tell us the percentages. For these two, that's 1 above. This whole space here is about 68%. And then here, the 2 standard deviations above and below is about 95%. And then here, 3 standard deviations is about 99.7%. All right, now, they want us to go down here to number 12. It says here, assuming, it says, man, I love M&Ms. Can't get enough of them. When I buy a bag, the last thing I want is to get shorted. So how many M&Ms is enough? According to a fascinating post on joshmadison.com, the mean number of M&Ms in a standard vending machine bag is 54.6, with a standard deviation of 1.3. Assuming that the number of M&Ms per package is normally distributed, which by the way is more than likely is, fill in the blanks in the diagram below, which represents the distribution of M&Ms in a standard package. Think number of M&Ms. Okay, first of all, they told us the mean is 54.6. So this is what goes here. They tell us the standard deviation is 1.3. So that means that every standard deviation you go up, you add 1.3. So this will give us 55.9. That's 1 standard deviation. For 2 standard deviations, we'll add another 1.3, and that'll be 57.2. And then another 1.3, which would be 58.5. Now from here, we will be going down. We have to subtract 1.3. So this will be 53.3. This will be 52. And then finally, this will be 50.7. Now for 13, it says if you buy 1,000 packages of M&Ms, a number I assure you I've surpassed in my lifetime, how many bags would you expect to have between 53 and 56 M&Ms in it? Okay, so if you look here, 53, this is very close to 56. So I would expect, first of all, it'd be 34.1%, 30 plus 34.1%, which is 68.2%. So I would take my 1,000 bags and multiply it by the 68.2%, which is 0.682. So this would be 682 bags. So it's likely that over 99% of all bags have between, if you look, 99%, that'll be from here at the 3rd standard deviation to the 3rd standard deviation. So that'll be between like 50 to 59. What percentage of bags would you expect to have at least 55 M&Ms in them? Okay, so it said at least 55. So with that being said, we would start off here, excuse me, at 13.6% plus 2.2%, and then plus this 0.1%. Now, when we add all of these up, I would expect 15.9% to have at least 55 M&Ms in them. All right, now we go here to the back to problem 16. It says, what percentage of bags have less than 52 M&Ms? How bad would that stink if you got one? Okay. All right. They say less than 52. So if we go less than 52, it'll be 2.2 and 0.1%. 2.2% plus 0.1%, that'll be 2.3%. Now for 17, how unusual would it be to get a bag with more than 58 M&Ms or less than 52? All right. Say more than 58 but less than 52. It'll be the 0.1, 2.2, and 0.1. 0.1%, 2.2%, and 0.1%. So that'd be 2.4%. Now we go here to the bottom. It says a quantity that can vary randomly from one individual trial to another, like the number of M&Ms in a randomly selected bag, is called a random variable. Why? Because it's random and it can vary. If you're really sharp, you may have thought about the connection between the percentages we've been calculating in this lesson and probability. If you haven't, we're going to ask you to do so now. Using what we know about area under a normal curve and percentage of data values, what does the area under the curve between two data values tell us about probability for a random variable? The area is the decimal form of the percentage. The decimal form is the probability. All right. Now it says, based on the work you did earlier, what's the probability that the next bag of M&Ms you get from a vending machine will have either 56 or 57 M&Ms in it? Okay, so they said 56 or 57, that'll be 13.6%. So it'll be 13.6%, which is equal to 0.136. We found the percentage in that range and changed it to a decimal. Now we come down here to what is known as z-scores. Now, z-scores, as you probably know, there are two main companies that offer standardized college entrance exams, ACT and SAT. Since each has a completely different scoring scale, it's really difficult to compare the scores of students that took different exams. Do you think that scores for these exams are normally distributed? I would say yes. Most people score close to the mean. With less as you get further from the mean. So basically what it's saying is, and I'll just use it on a positive side, the higher scores. When you look at people that get the higher scores on the SAT or ACT, is not that many of them. But it's a lot of people that score very close to the average. Okay, one way to compare statistics drawn from different populations is to compare how far above or below the mean they are. The z-score is a statistical measure that was designed to do exactly that. A z-score tells you how many standard deviations a data value is from the mean. The data value on the number line above would have a z-score of 1 because it is one standard deviation above the mean. Data values that are below the mean will have negative z-scores. Now it says here, fill in the blanks in the diagram with z-scores using the description at the bottom of the previous page. So basically, the mean will have a 0 z-score because it's not above or below the mean. It is the mean. But this here is 1 standard deviation away, 2 standard deviations, and 3 standard deviations below the mean. This is 1 above, 2, 2 above, and 3 above the standard deviation. So that's how the z-scores would look. Now it tells us a standardized test of intelligence is scaled so that the mean IQ is 100 and the standard deviation is 15. We'll be using these facts for the next few questions. Number 5, find the z-score for a person with an IQ of 85. Okay, so if you look here, the mean is 100, standard deviation is 15. So if you want to get to 85, 100 minus 15 is 85. So you went 1 standard deviation down because 1 standard deviation would be 15. But watch this. Well, let's just go here. So what we would do here, we would have the z-score is equal to -1 because that's 1 standard deviation below. Now it says find the z-score for a person with IQ of 115. So remember the mean is 100. We'll add 15, which is 1 standard deviation, so it'd be 115. So your z-score would be 1. Now number 7. What's the probability that a randomly selected person has an IQ between 85 and 115? So if we look here, 1 standard deviation above is 115. 1 below is 85. So we want to know the probability that a randomly selected person has an IQ between 85 and 115. That falls in between here. So that'll be 34.1% plus 34.1%, which is 68.2%, which is written as a decimal 0.682. Now it says here, if a data value has a z-score of 0, then half of the data are below that value and half are above. Number 9, we know that the center of a normal distribution is the mean for a random variable. What does question A tell you is also true about the center of the distribution? It is also the median. Because remember, the median has just as many values above as it does below. Because half is above and half is lower. So number 10, a job applicant is told that their IQ score measured in the screening process is higher than 84% of the general population. What was their z-score and their IQ? So if it's higher than 84% of the population, then what you would have to do is start from here and add until you get up to about 84%, which would stop here. So you have 0.1%, 2.2%, 13.6%, 34.1%, and 34.1%. Okay, now when you add all of that up, that will give you 84.1%, very close to the 84%. So if you look here, where we stopped here was at 1 z-score, at 1, well, when the z-score is 1, which is 1 standard deviation. So since we know it's 1 standard deviation, the IQ is equal to the mean plus 1 standard deviation, which would be 115. So 115 means that you're above 84% of the population. All right, now we come to this next page where we're going to physically compute the z-score. It says for a data value from a sample with mean x bar and standard deviation s, or from a population with mean mu and standard deviation lowercase beta, the z-score is, and we have this here. Now, let's go to this problem here. It says 1 year the ACT had a mean score of 21.2 and a standard deviation of 5.1. So let's write this up here. I'm going to write it up here. ACT, we know the mean is 21.2 and the standard deviation is 5.1. The same year the SAT had a mean score of 14.98 and a standard deviation of 347. Suppose that a scholarship committee is considering two students, one who scored 26 on the ACT and another who scored 1800 on the SAT. Both are pretty good scores, but which one is better? That's not so easy to decide because the scales are totally different. First instinct, which score sounds better to you? The SAT. 1800 sounds high and is 300 points above the mean. Now it says find the z-score for each test score. So we take the ACT. So our z-score will be x minus the mean over the standard deviation. So it'll be a 26 minus 21.2 all over 5.1. Now when we put this in our calculator, first of all, the numerator would be 4.8 over 5.1. So our z-score would be 0.94. It's a little short of one standard deviation. Okay, the SAT, the z-score, same thing, x minus x bar over the standard deviation. We had 1800 minus 1498 all over 347. That would give us 302 over 347. And our z-score will be 0.87. So we calculated the z-score for both. Now we come here. It says here, describe exactly what each z-score tells us. The ACT z-score was 0.94 and the SAT z-score was 0.87. So it tells us a 26 on the ACT was 0.94 standard deviations above the mean. Now with the SAT and 1800 on the SAT was 0.87 standard deviations above the mean. 14. Based on the z-scores, which would you say was a better score? Have to be the ACT score of 26. Had the higher z-score. So it was a higher score overall. Okay, now we only have just a little bit more to go here. We have basically, I think it's only 3 questions and then we're done with 4-7. Now, if we come down here, it says the 1942 St. Louis Cardinals were an awesome baseball team. They won 106 games in an era where teams only played 154 games in a regular season. During the 1942 season, the mean number of games won by a National League team was 75.8. So we know this 75.8 would have to be the mean. So the mean is 75.8. And then the standard deviation would be 20.5. Now this is the 1942 team. Now it says another great Cardinals team was the 2004 squad, which won 105 out of 162 games in 2004. The mean number, so this is 2004, the mean number was 80.9 and the standard deviation is 13.6. Okay. Now it says based strictly on winning percentage, the percent of games won, that is, which was the better team. Okay, so 1942, they won 106 out of 154 games. So they had a 68.8%. 2004, they won 105 out of 162 games, and it was 64.8%. So the 1942 team had the better percentage. Okay, now we move on to the last two problems. It says use information besides the winning percentages in the preceding paragraph to make a good statistical argument about which team was better. Obviously, showing your work is a must. Okay, basically, we don't necessarily have to calculate the z-score. We could look here because they want us to make an argument. If you look here, the 2014, yeah, let's do the z-score. That'll be easier. So we do the z-score for the 1942 team. The x minus the mean over the standard deviation. X is the amount of games that they actually won, which is 106. And the standard deviation was the mean was 75.8. And the standard deviation was 20.5. So we'll do the 2014 the same. So it's 105 minus 80.9 over 13.6. Now let's put this in our Desmos. So we'll have 106 minus 75.8 divided by 20.5. So that'll be 1.47 rounded to 2 decimal places. Then we would do the other, have 105 minus 80.9 divided by 13.6. So this would be 1.77. Yes. Okay. The argument, the 2014 has a higher z-score, which makes it have a larger standard deviation from the mean, which is better. Now, 17, it says, look back at your answer to question 1 on the first page of this lesson. How did you do? Would you be able to come up with more examples? Say we did pretty well. That's what we were naming the examples for, like things that were normally distributed. And I put IQ scores and some other things there. So we did pretty well. We can add height, weight, and candy in a package. And that is it for Math 130 for this semester.